One of the fundamental things that controls the way Bloodhound will behave on the desert is the forces that will be acting on it. And some of the biggest forces that will be acting on the car come from the aerodynamics, that is the flow of air over the vehicle. It's very difficult to understand how these forces are going to act at these extreme speeds. We're travelling faster than the speed of sound, so we're going to be generating things like shock waves. And traditionally we might have tried to understand how an object like this travelling at these kind of speeds would behave by using a wind tunnel. Instead, on Bloodhound SSC, we've used a thing called CFD. Now, CFD stands for Computational Fluid Dynamics. Basically, what we're doing in the world of CFD is virtual wind tunnel testing. To run supersonic wind tunnels is extremely expensive. And also, there simply aren't supersonic wind tunnels where you can model things like the rolling ground that we have in Bloodhound, the rotating wheels that we have in Bloodhound. What CFD allows us to do is to very quickly make design decisions in the design office, change the geometry of the car, and then find out aerodynamically what influence that has had. CFD is a fantastic tool for doing that. So, a fluid, which comes in the name, Computational Fluid Dynamics, is anything that flows. So air can flow. That's what the wind is doing when it blows. It's air flowing. So air is a fluid. The properties of that air are what we're trying to understand in aerodynamics. We're trying to understand how the pressure is varying, how the density of the air is changing. And also a fundamental property of air is its viscosity, or almost its stickiness, the way in which it can apply friction to a surface. So these are all properties of air flowing as a fluid that we're trying to understand in CFD. So at these kind of speeds, air is a compressible substance, so it has the ability for its density to change as it flows around the car. And the equations that describe high-speed compressible flow around something like Bloodhound are known as the Navier-Stokes equations. Two physicists, scientists came up with these equations, Navier and Stokes, and in fact these equations have been around for hundreds of years. But until very recently, we haven't known how to solve them. Essentially what we're doing in CFD is solving a complex set of equations that describe the physics of high-speed aerodynamics. It is in fact so difficult to come up with an exact solution to these equations that there's a mathematics institute in America right now offering anybody a $1 million prize if they can come up with a single exact solution to these equations. So it is an incredibly difficult thing to do. So we have to introduce approximation. Now, any complex problem in science, in maths, even in life, a good philosophy for solving that complex problem is to try and break it down into smaller, more manageable chunks. And that philosophy really is behind CFD. So what we create is what we refer to as a mesh, a computational mesh, where basically we break down the three-dimensional space around the car that we're studying into lots and lots and lots of very small 3D shapes. Because there are so many of these elements, we have to use an incredibly big, powerful supercomputer in order to solve the equations. So we solve the equations element by element, with each element talking to its neighbours, and we evolve within a supercomputer towards an approximate solution of the Navier-Stokes equations. Essentially what comes out of a CFD package is streams and streams of numbers, millions and millions and millions of numbers. What we have to do is then turn those numbers into something that you can actually visualize with your eyes. So we use what's known as a post-processing package. It's a commercial software package that basically turns those numbers into something that you can see. And these are the pictures that we've come to know looking at the Bloodhound project of pressure distributions over the desert surface and over the car. Usually we will visualize the pressure distribution over the car using colors. And typically, and for example in this image here, the red represents high pressure and the blue represents low pressure, and then there's the spectrum of pressures correlating to the spectrum of colors in between red and blue. So straight away you can look at that and understand how the air is flowing around the car, where the shock waves are forming, things that are of interest to us. Lots of people often wonder why we can trust numbers that are coming from CFD because we're doing everything in the virtual world. Well, of course, what we have to do is validate the simulations that we run. We have to validate the techniques that we're using to understand how accurate our CFD simulations are. A famous test that we did to demonstrate that CFD really does work was back in the 1990s, the Pendine rocket test that Ron Ayres set up, which proved that the CFD system that we're using at Swansea actually is generating numbers that are reliable and we can trust. And we'll be doing a similar validation study for Bloodhound when the car starts running. We'll be taking data from the car and comparing it with simulation data from the CFD analysis and making sure that those two match up.
When I started designing the thrust SSC back in the mid-1990s, I was told by many experts that computational fluid dynamics could not be trusted. And as we had someone's life at stake, I thought we must validate it somehow. So we designed a rocket sledge model of thrust and accelerated it up to 800 miles an hour in 0.8 of a second and measured the pressures on it so that we could compare those with the computational fluid dynamics. And the comparison was so good that we were happy to continue with the design of thrust SSC. To accelerate the car to those speeds, we had a total of 22 rockets on the car. These were date-expired boost motors from air-to-ground strafing rockets. As they were date-expired, we kindly volunteered to use them up.